question. Let's see. Okay, it is working. Great. Okay, so I'll begin where we left off. We'll be starting by talking about the technical overview of the paper. So we'll try to talk about roughly how we prove this lifting framework. So recall what we want to show is that we have a good linear sketch, good streaming algorithm, linear sketch for discrete inputs, discrete Gaussian plus some distribution. Then we can create another linear sketch, which has roughly the same number of rows up to a constant factor, and it will be correct with high probability for continuous Gaussian inputs. Then we can lift the lower bounds as David explained. So let's begin with some notations. We'll let D sub Ls be the discrete Gaussian distribution on the support L will be a lattice, with the covariance matrix S transpose S. And throughout the talk, we're going to suppose that we sample X from a discrete Gaussian supported on the integer lattice, C to the N, with covariance S transpose S. And Y will be sampled from discrete Gaussian on the lattice imposed by A times E to the N, with the corresponding covariance after I multiply by A. Now, if we want to sort of mimic what happened in the continuous case, we want to show some sort of approximate rotational invariance. We want to show that the total variation distance between AX and Y is very small on the support A times E to the N. Begin. Unfortunately, this is not true in general, and we'll see why on the next slide. So let's look at this example. Let's say we're just in 2 dimensions, and we sample X from a discrete Gaussian supported on Z squared with identity covariance, and Y again from the discrete Gaussian on A times Z squared with the corresponding covariance A times A transpose. And let's just pick this super simple matrix with just 1 and n in the columns. Then if we look at the right picture here, if I just multiply A times X, I'll just get the first coordinate plus n times second coordinate. And we get this plot for x1, x2 sampled from discrete Gaussian. And if I sample Y directly from this discrete Gaussian distribution on support A times Z squared, and this will have a covariance 1 plus n squared, then we get this very nice bell shape where the mass is uniformly distributed around O of n. While here we had these strange spikes that really upweighted the second coordinate. So in fact, in this case, it's a bad example. We have a very large total variation distance between AX and Y in large parts of the PMF. Yeah.
Can you expand inclusion? Why?
Yeah, I guess you can think that like if A is like a very irregular matrix, it has some kind of like, I don't know, it kind of like gives a lot more weight to certain coordinates than others, then it might cause these like irregularities when you multiply by this discrete input x1, x2. While if I sample directly from discrete Gaussian, it's sort of like a continuous Gaussian PMF, but only at integer points. So it has a much more smooth PMF.
Yeah, if you think of x1 and x2 as like small constants. So AZ squared here is just like a set of points.
A times Z squared is the lattice.
Okay.
Yeah.
So consider it as a set without any sort of grading.
Sure, yeah. Yeah, any other questions about the system?
Is C squared 1 dimensional, 2 dimensional?
It's so it will be 1 dimensional.
Then A transpose is 2 dimensional.
A transpose will be so it'll be just n1, and then if I multiply A transpose, it's 1.
Oh, okay.
Yeah.
Sorry. That makes sense.
Yeah, any other? Okay. So as we see here, there are some bad examples where X and Y are not close in total variation distance. So the natural question is to try to consider which conditions do we need on the sketching matrix to say that AX and Y are close. This is what we're going to address using lattice theory on the next few slides. To do that, we're going to need to define some quantities that are going to show up many times throughout our work. So first, we'll need to define this ith successive minima, lambda I of L, where L is a lattice. And it's defined as the smallest value so that the ball of this radius, centered at the origin, contains I linearly independent vectors that span the lattice. Or not completely span, I linearly independent. And second, this L perp of A will be the lattice containing all integer vectors which are orthogonal to the row space of A. Any questions about this? I'll have an example next. So let's just focus on the same matrix we had before. A is just 1 and n. Then if we want to find out what is the orthogonal lattice to the row space of A, well, we should try to find vectors that are integer vectors that are orthogonal to the only row. So the answer is -n1 is one of the vectors. And lambda1 of L, well, this is the smallest radius such that it contains the row 1n. So it has length square root of 1 plus n squared. Okay, so now that we have these two quantities, we'll be able to define the sufficient condition for when ax and y are small. And this comes from a very nice work of Adversarial and Regev in 2016. So what they show is, if we suppose that some condition is true, I'll parse it in a second, then actually it is true that the PMF of ax is very close to the PMF of y. So this is exactly what we want, but modulo this condition. Now we should figure out what the condition means. So what we have here is the smallest singular value of S. Remember, the covariance was S transpose S. This should be at least lambda max of the orthogonal lattice. Lambda max will be the maximum successive minimum of the lattice. It's the smallest radius such that the ball centered at the origin contains all of the basis vectors for that lattice. And L perp of A was the orthogonal lattice to the row space of A. So basically, if the smallest singular vector of our covariance matrix, which we have control over the covariance matrix, so we can make that happen, this is at least lambda max of the orthogonal lattice times some polylog n factor, then we would be able to get this kernel variation distance. And especially if we set epsilon to be 1 over poly m, then the sketching matrix will sort of pass through to the covariance as we go. Any questions here? Okay. So let's recap. This paper of Agrawal and Regev requires this condition. So as I said, we can scale S so that the largest singular value of S is at least poly n. Smallest singular value of S is at least poly n. And then all we would need to do is upper bound lambda max of the orthogonal lattice by poly n. Unfortunately, this is also not true in general. So we'll see an example on the next slide. So just to parse what this means, the maximum length vector of the basis for the orthogonal lattice needs to be bounded by poly n. Unfortunately, we'll see an example where there's a vector in the orthogonal lattice which has exponentially sized entries. So here A is defined as follows. We have a 1 in the first non-zero entry of every row, a -2 in the second non-zero entry, 0 is everywhere else. So if you stare at this for a little bit, you'll see that if you multiply A times this vector, then you will get the all zeros vector. So this vector with exponential sized entries is actually in the kernel. So it's in the orthogonal lattice to the row space of it.
And generates the kernel?
It's
Is that the only way back in kernel? Or the only way? That's right.
It's the maximum.
Yeah, so it has exponentially large entries. We can't bound this by poly n. So what should we do? It seems like we're stuck here. But the key observation we use is actually, without loss of generality, when we prove the lower bound, we can assume that the algorithm actually did some pre-processing and added some extra rows to its sketching matrix. This only makes the sketching matrix stronger. It only observes more information, potentially. So we can just assume we proved the lower bound against this new modified sketching matrix. So what we'll do is exactly what I said. We'll pre-process A to a matrix A prime, which has roughly the same number of rows as our framework suggests. And now the condition lambda max of the orthogonal lattice will be satisfied. It will be bounded by poly n. Okay, let's see first attempt to do this. So there's a very nice lemma called Siegel's lemma, which says the following. If I have any matrix, R by n matrix, with integer coordinates, and R is less than n, I have fewer rows than columns, And let's say all of the entries in the matrix are bounded by some parameter m. Then I can always find a non-zero vector x with all of the integer coordinates bounded by this quantity, so that this vector is in the kernel. So it'll be in the orthogonal complement of the row space of A. So in particular, this lemma suggests a natural preprocessing approach. What we could do is we could iteratively find these vectors x and then add them to the span and then continue applying Siegel's lemma. And hopefully all of the vectors that we add have bounded bounded coordinates. So let me explain it in more detail. What we will do is we will use Siegel's lemma to preprocess A. So we have more rows than R. It actually won't be O of R, but we'll start with this. And this lambda max condition will be satisfied. Let's see more precisely what this means. So let's start with A sub 0 being just the original sketching matrix A. And then in each time step, let's say we have a matrix AT. We will apply Siegel's lemma and find this vector xt so that xt is in the kernel of A and it has bounded entries. So it has a bounded norm. And then we'll add xt to the matrix itself, to AT, and form the next matrix, AT plus 1. And then we will apply Siegel's lemma again and continue generating all of these vectors. So we'll repeat this process roughly 0.49 n minus r times. To give motivation for this number, this is the number of times that we can apply it and actually get vectors that have polybounded entries. After we go further, actually this quantity will get too large and we won't get vectors with polybounded entries. So yeah, we will apply this 0.49 n minus r times, and we'll have that all of the vectors xt which we generated have entries that are bounded by nm. And then we can continue applying Siegel's lemma and generate all of the remaining vectors, 0.51 n vectors, y1 through y 0.51 n. And remember, as I just said, these vectors might actually have unbounded entries because of the bounds in Siegel's lemma. But what we will do now to finish the preprocessing is we will take these last vectors, which may have unbounded coordinates, they might be exponentially large, and we'll add these vectors to A to form the new matrix A prime. After we do this, just by definition of how we did this, the vectors that are in the orthogonal lattice to the row space of A will actually be exactly the xt's, and they have polyunbounded entries. So basically, after this preprocessing, we achieved the goal that lambda max of the orthogonal lattice is bounded by polynomial nm. Any questions about this? Yeah.
Do you have any intuition, like if instead of doing this very interesting process, if you just added like random rows, random integer rows, would that also avoid like these exponentially sized vectors in the
yeah, that's a great point. So we will do something very similar actually in the probabilistic argument. We will have another preprocessing, which will do something like that. Yeah.
So A prime now is unbounded entries, but that's not.
Yes, yeah, it's not an issue, because it only gives the algorithm even more power to observe information. Yeah, the original matrix A was polyunbounded, but the new matrix after preprocessing can be unbounded.
So you basically like found like small independent vectors next to the complement.
Yes, we found the small vectors, and then we made sure that they would be in the orthogonal lattice after adding some other vectors. Yes, good question.
So did we need to use single lemma to get those 0.51 n vectors, or could we make any orthogonal vectors? Like
Sorry, I didn't.
for the last 0.1 for the y eyes, we just pick whatever orthogonal vector we want, or is it just
Yeah, I guess you can, yeah, because we don't care about the bounds, yes. Okay, so this is what we did, and we, as I said, A prime will now satisfy the condition for TBD closeness because we have satisfied lambda max of the orthogonal lattice being bounded by poly n. So then we can apply Augerwal and Regev's paper directly. But as we might have noticed, we added a lot of rows. We added constant times m rows. And in this case, we won't be able to prove the same lower bounds that we have in our lifting framework. In particular, if the lower bound we want to lift from continuous to discrete setting is less than n, then we won't be able to lift and get the optimal bound. So we'll really need a better preprocessing for this. What we're going to do is this. Here we have the full basis for the n-dimensional space. And this is roughly what we want. We start with the row space of A being r-dimensional. Row space of the orthogonal lattice to A is n minus r-dimensional. We will construct, using some probabilistic argument, n minus 4r linearly independent integer vectors in the orthogonal lattice, which have bounded norms. And then we will construct iteratively, say using Siegel's lemma or any other way, the remaining 3r integer vectors. And then we will add those 3r vectors to A prime and form the new reprocessed matrix A prime, which will only have a constant times number of dimensions. So now the key thing we need to talk about is how to construct this using a probabilistic argument, n minus 4r linearly independent integer. And yeah, so because by what's written here, we actually will get this condition. Lambda max of the orthogonal lattice will be found. Okay, so what we'll do is the following. Let's suppose that we've already found t vectors, which are linearly independent in the orthogonal lattice of A with entries bounded by poly n. And let's define this matrix B to be an n minus t by n matrix, where the rows of the matrix form a basis for the orthogonal complement to the span of the t vectors that we found. So this is what we're going to do. We're going to randomly pick roughly n to the O of our vectors vi with entries in this range, 0 to m. You can think of m as a polynomial in n. And the first event that we want to say happens with high constant probability will be that there exists some pair ij, so that A times vi is equal to A times vj. The reason for this is, now if you notice that vi minus vj will be in the kernel of A, so it will be in the orthogonal lattice to the row space of A, since vi and vij are integer vectors. So the first thing to notice is this event I holds with high probability. The entries of AVI are all bounded by poly n, so there are like roughly poly n possible values for A times VI, so you can apply the birthday paradox, say with high probability, there will be some collision. The second event is that for all of the possible pairs ij, that B times Vi is not equal to B times Vj. So if I rearrange this, B times Vi minus Vj is not equal to 0. Vi minus Vj will be not in the kernel of B. So it cannot be represented as a linear combination of all the previous vectors. And actually, event 2 also holds with high probability. We can see this by writing B in a reduced row echelon form, and then you can check that this probability bound is satisfied. Basically, you need to make this cancellation work exactly. And then you can union bound over all pairs ij. So event 2 is also holding with high probability. Let's summarize what this says. So with high probability, conditioning on event 1 and 2, then Vi minus Vj is actually the vector that we wanted to find. It is in the kernel of A, so it's in the orthogonal lattice to the row space. And it's also not in the kernel of the rows in the orthogonal lattice, which we already found, since B times Vi minus Vj is not equal to 0. So we can apply this probabilistic argument repeatedly until we've done it already n minus O of r times. And then after we've done that, we can use Siegel's lemma to generate the remaining integer vectors that are orthogonal to both the row span of A and the vectors that we found. Then finally, we will just add these O of r vectors, which might have very large coordinates, again, to the span to the matrix A, and form the new matrix A prime, and it will satisfy the requirements since all of the other vectors in the orthogonal complement had polynomially bounded entries. Any questions about it? Yes. So next we'll talk about the remaining ideas in the proof. So recall that we sample x and y this way. X is coming from a discrete Gaussian on the integers, and y is coming from discrete Gaussian supported on a times z to the n with the corresponding covariance. And let's additionally sample z from a continuous Gaussian with the same covariance as x. So by all of our preprocessing, we can assume that the orthogonal lattice to the row space of A has bounded successive minima. This is what we ensured through the preprocessing. And now let's let this small eta be a uniform noise in one unit cell of the lattice. What we want to show is that the distribution of AX plus eta with the noise is very close to a distribution of A times a continuous Gaussian. We'll do this through a sequence of steps. First, we'll show that distribution of AX plus eta is very close to the distribution of Y plus eta. This actually follows directly from the preprocessing, and by applying the theorem of Agrawal and Regev, we know that AX is close to Y. Next, we'll show that the distribution of Y plus eta is very close to a continuous Gaussian with this covariance. And this is actually exactly the distribution of A times Z, since Z is a continuous Gaussian, and it has rotational invariance. So by linking all of these arrows together, we get that AX plus eta is very close to AZ. But now you might be concerned, why is it that we're looking at AX plus eta? Since actually we're all thinking about discrete sketches, we should have discrete inputs. Why do we have this strange eta? Well, discrete sketches take AX as the input, but AX can be recovered from AX plus eta, since we can just bake in the rounding in the pre-processing, post-processing step. So the algorithm can actually receive AX plus eta, and then it can choose to round to the nearest lattice point, and then apply the estimator function. So this is without loss of generality. Then we can assume that the discrete algorithm actually saw AX plus eta. So in particular, the algorithm should also work if it sees A times Z, which, as we said, is very close to AX plus eta. So this sort of completes the proof at a high level of the lifting theorem. Okay, so we applied this lifting framework to obtain optimal lower bounds for a variety of problems, as David said. And we also apply it to the to proving lower bounds for adversarially robust streaming algorithms for LP estimation. So this nice work of Hart and Woodruff in 2013 showed that linear sketches for LP estimation are not robust adversarial inputs, meaning they need to have roughly n dimension to answer polynomially many adaptive queries. And the attack works by approximately learning the sketching matrix A and then querying something either 0 or something in the kernel of A with half probability. And the idea is that the algorithm will not be able to distinguish between these two cases, and it will not be able to give a constant vector approximation. So this attack works in an iterative way. It starts with the approximate row space V1 being the empty set. It doesn't know anything about the approximate row space. And then it will try to iteratively build up an orthonormal basis for the approximate row space. So the first step of every round will be to find many vectors that are weakly correlated with the row span of A, but orthogonal to all of the previous vectors that we found before. Then the next step will be to use these weakly correlated vectors to find a strongly correlated vector V, which is very close to being the row span. And then finally, the attack will make progress by setting Vi to be the span of all of the previously bound vectors and V. So what is the correlation finding step work? What it does is it will start with the current subspace we know so far, and then we will iterate over small increments of this parameter sigma squared. So we'll sample many VIs from the discrete Gaussian with a particular covariance. This covariance will be the matrix that projects onto the orthogonal complement of all of the vectors that we found so far, and potentially scale with this parameter sigma squared. And then we will compile all of the examples that the algorithm said yes on. So the algorithm needs to decide, is the norm very large or is it very small? And then after finding all of the weakly correlated vectors, the algorithm will find the top, it will put all of the vectors into a matrix and find the top right singular vector of that matrix. This will be V sigma. And this vector will be very close to being in the row span of A. So additionally, if that vector satisfies some condition that it's very strongly correlated with the row span with some gap, then we will actually add this vector to VI. So yeah, I think I roughly said what the algorithm will do. I won't go through every step. But yeah, at a high level, it will if for every round, it will it will go through many increments of the variance of the sigma squared. It will sample all of the queries from a discrete Gaussian in the space which is orthogonal, the Gaussian on the space which is orthogonal to everything that it has found so far. And it will query the algorithm of all of these vectors, find the answers, and then find weakly correlated vectors, and then try to compile it into a strongly correlated vector, which is very close to being in the row span. So this is actually exactly what the attack did in the continuous setting. So what we need to do now is we need to prove that for every round T, there will be some sigma squared so that we can find this strongly correlated vector. And this is exactly where we use the lifting framework. So we'll show that there exists a variance sigma squared so that the expectation of the projection, so the expected norm of the projected query, given that the algorithm says 1, is at least delta plus the expected projected norm. So sort of as David explained, the intuition is that if the algorithm is given a query that's very close to the row span, then it might get confused and it might think that the query's norm is larger than it really is just because the projection is larger. So then we will be able to find some variance so that the algorithm will become confused. So this is exactly the lemma that's shown in the continuous paper. And we prove this by simply lifting to the continuous version of the conditional expectation lemma. So in particular, what we do is we say, suppose that this is not true in the discrete setting. Then we're able to come up with a slightly adjusted estimator so that we get a contradiction with the continuous conditional expectation lemma. So that's a contradiction with the previous Hartwig paper, and that's how we conclude this conditional expectation lemma. Okay, so finally, to summarize, overall, we gave a framework for lifting linear sketch lower bounds from continuous inputs to discrete inputs. And the idea was to use discrete Gaussians in place of continuous Gaussians on certain well-behaved sketches where we apply this preprocessing. And as we saw, we can use this technique to achieve lower bounds for a range of problems and potentially for more problems that we didn't consider. And future directions could be to look at lower bounds for streaming beyond integer linear sketches for certain problems like operator norm and PSD testing, etc. But on the topic of this workshop, it would be very interesting to design attacks on streaming algorithms for L0 estimation or for LP estimation. Or in general, to prove that we can close the gaps between upper and lower bounds for these. That's it. Yeah, thank you.
So you use this result of Gribelyuk and someone else to like get the initial reduction from X to Y. Do you have intuition for why?
Why this condition?
Or why the condition is sufficient?
Yeah, it's a good question. The proof is pretty simple actually in their paper. I don't quite remember why exactly this condition is.
Or I guess why is the like maximum like size or something possible?
Yeah, it's a good question. I don't quite remember. Yeah, I can check and then talk to you about it. Yeah.
Yeah, this is like unrelated to the main contribution, but what is the complexity of like running Siegel's lemma?
I think it's not efficient, but we don't really care about efficiency.
Right.
For the proposal. We just want to say that there exists a frequency.
If the probabilistic argument you're generating entity or the
Oh yeah, that already breaks, but I know, I'm just curious because it's such a nice primitive.